Ever wonder what makes gold so shiny? Or what makes oxygen so essential for life? Turns out the answers are hidden in a kind of secret code, a unique address for every single electron in every atom. In this explainer, we're going to crack that code. We're going to uncover the fundamental rules that literally build our entire world from the ground up.
And it all starts right here with this chart. I mean, we've all seen the periodic table, but let's be real, it's a weird shape. Why isn't it just a simple, neat grid? What's going on with these strange towers in those sunken-in valleys? Well, the answer is that secret electron address, and by the end of this, the logic behind this bizarre shape is going to be perfectly clear. I promise.
So, here's our game plan. First, we'll figure out what an electron's address actually is. Then, we'll dive into the 3 golden rules that they all have to follow. We'll use those rules to map out this electron city, build a configuration from scratch, and even look at the really cool exceptions that make chemistry so fascinating. All right, so what exactly is this secret address? Well, in chemistry, we call it an electronic configuration.
The best way to think about it is like a unique home address for every single electron inside the huge city of an atom. And this address does way more than just tell you where an electron is. It dictates the atom's entire personality, how it acts, what it bonds with. This is literally the blueprint for all of chemistry.
But you know, this atomic city isn't some kind of free-for-all. Oh no. It's got these super strict zoning laws that every electron has to obey. Let's break down the 3 big ones. First up is the Aufbau principle. You can just think of this as the lowest floor first rule. Imagine you're filling an empty apartment building. You wouldn't start on the top floor, right? You'd fill the ground floor first because it takes way less energy than climbing all those stairs. Well, electrons are just as lazy or efficient. They always take the lowest energy spot available before moving up.
Next, we have Hund's rule, which I like to call the personal space rule. So picture a set of empty apartments all on the same floor. That's what we call a sublevel. When new tenants, our electrons, move in, each one is going to grab their own empty apartment before anyone has to get a roommate. It's just more comfortable that way. So electrons fill empty orbitals one by one before they ever pair up.
Okay, and check this out. Here's that rule in action. See those 3 horizontal lines? Think of those as 3 empty rooms on the same floor. The arrows are our electrons, so watch what happens as they move in. 1, 2, 3. Each one takes its own space. It's only when the 4th electron shows up that it's forced to pair up with another one. That's Hund's rule, plain and simple. And the 3rd and final rule is the octet rule. And this is the end game for most atoms. The ultimate goal is to get a full outer shell with 8 electrons. That configuration is super stable, it's like chemical nirvana. And to get there, atoms will do whatever it takes. They will gain, lose, or share electrons. And that whole process? That's what we call chemical bonding. So we've got the zoning laws down, but how do we know which streets and houses to fill and what order? For that, we need a map. And as it turns out, we have 2 incredible ones. Our first map is this, the Aufbau diagram. And this thing is our master key. You just follow the diagonal arrows. So 1s, then 2s, then 2p, then 3s. But wait, here's where it gets a little weird, right? Look how the path goes down to 4s before it loops back around to fill 3d. This shows us something super important that you wouldn't guess. The 4s sublevel is actually lower in energy than the 3d. This diagram is essential because it shows us the true energy filling order, not just the numerical one. And our second map? Well, it's been staring us in the face this whole time. The periodic table itself. Those strange blocks are not random at all. They correspond perfectly to the S, P, D, and F sublevels. As you read the table from left to right like a book, you are literally watching the electron orbitals fill up, one by one, exactly according to the rules. The periodic table is a physical map of electron configurations. How cool is that? Okay, enough theory. We have the rules, we have the maps. It's time to put this into practice and actually build an electron configuration. Let's try zinc. It has 30 electrons that we need to find homes for. So we just follow our map. 1s gets 2 electrons. Then 2s gets 2. The 2p sublevel can hold a maximum of 6. We just keep going, filling each sublevel in the right order until we've used all 30 electrons. And here's the proof. If you add up all those little superscript numbers, you get exactly 30. It's a perfect accounting system. Now, as you can probably imagine, writing all that out for a huge atom would get pretty tedious. So chemists have a really clever shortcut. Let's take sodium with 11 electrons. We find the noble gas from the row right above it. In this case, neon, which has 10 electrons. We can just write Ne in brackets to represent that stable, filled core. Then all we have to do is add the leftover electron, 3s1. It's so much cleaner, and it lets us focus on the outermost electrons, the ones that actually do all the interesting chemistry. But just when you think you've finally mastered the rules, chemistry loves to throw a curveball. It turns out sometimes the filling order we just learned gets broken, and it gets broken for a very, very good reason: the universal drive for stability. This brings us to the stability rule. This rule says that an atom is in a special, low-energy, extra-stable state when its sublevels are either exactly half full or completely full. Think of it like a preference for perfect symmetry. This state is so desirable that an atom will sometimes actually break the Aufbau principle just to achieve. Take a look at chromium. Now, if we just follow our rules, we'd expect the configuration on the left, ending in 3d4. But that's not what we actually find in nature. Instead, an electron from the 4s orbital gets promoted. It literally jumps over to the 3d orbital. Now, why on earth would it do that? Because the configuration on the right, with a half-full 4s and a half-full 3d sublevel, is a more symmetrical, lower energy, and therefore much more stable state. The atom literally rearranges itself to find a more comfortable home. So this push for stability is a really powerful force. For chromium, stealing an electron from the 4s to make a perfectly half-filled 3d5 subshell is just a better deal, energy-wise. And it's not a one-off thing. The exact same logic applies to copper. We'd expect it to end in 3d9. But by promoting one electron, it can achieve a 3d10 configuration, a completely full d subshell. That extra stability is totally worth bending the rules for. And so we come full circle, right back to our original mystery. Looking at this map again, it's not a strange shape anymore, is it? We can finally see it for what it really is. The S block on the left, the P block on the right, the D block transition metals in the middle, and the F block down below. The entire architecture of the periodic table is a direct, visual blueprint of the invisible rules governing an electron's address. Mystery solved. And here's the ultimate payoff. This is why elements in the same vertical column act like chemical families. It's because they all have the same outer electron configuration. Just look at the noble gases over on the far right. They all end with that perfect full S2p6 octet. They're stable, they're noble, and they're famously unreactive. An atom's outer address doesn't just describe it, it defines its entire chemical destiny. So we've seen how just a few simple, invisible rules can generate the beautiful, complex, and ordered structure of the entire periodic table. It really makes you wonder, doesn't it? What other parts of our world are secretly governed by a handful of elegant, underlying principles, just waiting for us to find them?